Okay, so I guess it's a good time to start. So welcome everybody, and today we have Yang, and he was recently promoted to research assistant professor at the University of Hong Kong. So congratulations, Yang, and yeah, we are very happy to have you here today discussing how to generate lump hydrological models, and the floor is all yours.
Okay. Can you see the screen sharing?
Yes, we can see your PowerPoint.
Okay.
Yeah.
So thanks, Leila, for introducing me, and thanks everyone for coming. So good morning, good afternoon, or good evening to everyone. So yeah, today I'm going to talk about our work on learning to generate lump hydrological model, which is using generative AI to do hydrological modeling. For this presentation, please raise your hand or interrupt me if you have any questions we can discuss before we go too far. So this work is between me and my supervisor, Dr. Chui from University of Hong Kong.
One second. Leila, did you start the recording?
Yes, I did. It is recorded.
All right, sorry.
Okay. So in the front page, you can see a AI generated painting, which is very beautiful. It's generated by you.com. You just write a simple prompt to the system. It will generate a good looking pictures. So we are trying to use this power to enhance hydrological modeling. So before we start, let me show you our web applications developed based on the paper result. So we have two web applications. One is for prediction and another is for calibration. So let's go here. The link of these two web applications has been sent to the group email, so you can check in the email. This is acting like this is a local website on a local server, so you can see this one is a generative hydrological model. This model uses only 8 parameters to characterize a catchment, so you can modify the parameters and can see the predicted hydrograph show in green change in real time. And you can change the display window as well to get a closer look. And for now, you can select from 500 US catchment included in the camels. And you can also upload your own catchment files, which is similar to a conventional lump hydrological model. And this model is purely generated from data without human derived knowledge in hydrological processes. And this one is another applications for model calibration. So basically, you upload your calibration period, time series, climate forcing and discharge, and also the test period, discharge and climate forcing time series. Select a certain hyperparameters for your genetic algorithm to optimize. Then you can check the result, the calibration result for the test period as well as for the training period. So yeah, I'm going to show you how this web application is developed. So to begin, let's have some very general and brief definitions on generative AI. So a generative model simulates how the data is generated in the real world, which is a very simple and broad definition. So it aims to solve more general problem of learning a joint distribution over all the variables. So it models all the variables that occurred during the generation processes of the observation data. And a discriminative model, which is commonly used in our current hydrological modeling, is to learn predictors given some observations. For example, a conventional LSTM modeling framework faces this description. So if we provide a rainfall time series, we hope the model can predict the discharge. So we have a goal in our mind. So we want to build predictors for given observations. Here is some concrete examples. So for a problem that we have is that we have a 2D surface. On the surface, we have a certain point. So based on the point coordinates, which is location X, we want to predict the color of the point. For now, we have a red circle. We want to know the color, and the other reference point, the color unknown, as shown in the figure. So if we want to solve it in a discriminative approach, so we just train a simple conditional distribution model to predict the probability of Y, which is the color, given the location X. So we can predict probability of Y given the location of the red circle using the model. We can build from this given data, we can build a simple classifier that made a split at the middle of the screen. So we can see that given the location of the red circle, the point being blue is very highly certain. So this is called a discriminative approach. We only model the interactions we interested, which is Py given X. But it missing some information about uncertainty and the generative processes. For generative modeling, we additionally model a joint distribution Px and Y that could be further decomposed as P of Y given X times Px. So which means we additionally considered how the probability of the point, the density of the point on this 2D surface, as shown in this blue and orange circle. We have a high density range. So points within this range are more likely or more probable. So this point, we have a low confidence they will occur in this area. So although we according to our classifier, the point being blue is probability is high, but the probability we observe this point is low. So it is uncertain decision. Here we can compare the difference. So for generative modeling, we have an additional component, which is P of X. So we model the generative processes, how the data is generated. It's unlikely the point can be located here. We can sample randomly in this a point from the 2D space, and we can select the ones that are highly probable. So this is a generative AI model. We can generate new data point. So here comes the features of generative models compared to the conventional model. So for a generative model, it always involves modeling additional variables or variable interactions beside the discriminators or beside the predictors we are interested in, which is given some input, we want the model to predict some output. So in some cases, we also want to model P of X such that we can determine whether if input is often or is rare or is expected. And the second feature is that it provides a way to create new object that does not exist before. So we can sample from PX to get new instances or new object. So let's look at how can generative AI solve a hydrological modeling problem, particularly in rainfall runoff modeling. So in rainfall runoff modeling, the variables involved are climate forcing, discharge, and catchment functions F, which is quite abstract. It can be related to catchment physical properties like slope, elevation, climate zone, etc. So these three variables have the following relationship. Q can be expressed as a function of climate forcing. So now we have 3 variables. So commonly, we only model how the climate forcing is transformed to Q, which is like P of Q given climate forcing. If we want to do generative AI, we can additionally consider modeling P of climate forcing or P of catchment function. So it is quite straightforward to model climate forcing using generative AI, which is a P of climate forcing. So it's determining how frequent can a climate event being observed, such that we can have more confidence whether our prediction is for a novel event or for a regular event. But how can we model catchment function? So this is also the central topic of this presentation. So we are going to show a way to model catchment function. And based on the definition and some previous literature, they suggest that modeling in the science is almost always generative modeling. So they consider almost all the process-based models in science are generative modeling. So why is that? So let's have a simple example, which is a single bucket hydrological model, which has 2 parameters. One is storage capacity, another is groundwater recharge rate, as shown by this bucket. And we can plot the model's parameter space. On the x-axis, we have 1 parameter storage capacity. On the y-axis, we can have the other parameter, groundwater recharge rate. And the points are randomly scattered in this space. We can select some point to create a model like this one. We can select another point to create another one. So from this, you can see that although we are interested in rainfall runoff, those 2 parameters, but we additionally consider another 2 parameters, which is storage capacity and groundwater recharge. So this fits the first definition, which is considering additional parameters that can potentially explain the generation processes. And secondly, it provides a way to create new things, new object that has not been observed. So we can sample from this random space and create a new model. So that's why the lumped hydrological models are almost always generative models. If we compare to the deep learning models currently being used in hydrological modeling, they are mostly not generative. For example, this is a simple LSTM network, which fits in the climate forcing. So Jonathan, you have a problem?
I'm curious, that statement, can you explain, is this like a formal statement, or is this like a proposition? Or yeah, can you explain this statement a little bit more and explain if you mean it literally, or I just don't understand.
Okay, so the authors
I get the example you gave, but like, is this something that is literally the case with most models, or is this just like they can be thought of as generative?
Yeah, I think the author means they are generative models, but not generative AI. They also give definition on what is generative modeling at the beginning, and they use a climate model as an example. They said that all the climate models, and they then extend to ecological models and economic models. They said that they involve like latent variables and hidden variables that are hypotheses and can explain the generation processes. They term that as generative modeling. I think different people may have different interpretations. They also make very simple, let me go to the first slides. Simple definition of generative AI. They said a generative model is to model how the data is generated in the real world. So the definition is very broad. So if we model how the data is generated in the real world, even if not reality, it is only a hypothetical statement, it may still be considered as a generative model. I think other authors may have different definitions, but according to the definition of these two authors, hydrological models are generative models.
Okay, great.
So, no, this is a good discussion. So because everything else depends on this, let's just clarify. So, yeah, in that sense, what we're saying is that we have a process that generates hydrological responses, like a catchment process or something. And you're saying that you can then treat catchments as coming from some distribution of catchments. And if you observe a particular streamflow record, that's a particular realization generated by this distribution. Yeah.
Yes.
By tuning certain parameters or tuning certain conditioning on certain parameters or variables. That's interesting. Okay.
Yeah, interpretation is absolutely correct. So let's continue to looking at the deep learning models currently being used in hydrological modeling. So this is a simple LSTM network. At each time step, we fed in climate forcing. Then we have a hidden state, which can then be separated into a cell state and a hidden state, then pass through the future time steps to generate predictions. The model basically is trained to update the model network parameters, which can be tens of thousands parameters. And once the model is trained, we rarely adjust the parameters to create new models. So although it involves additional variables like neural network parameters or some hidden or some combinations of the neural network parameters, some people extract the combinations of the neural network parameters to link to hydrological concept, but rarely they haven't been adjusted to create new model. So deep learning models are not generative models, mostly in current hydrological studies.
So is that because it's one single model that we're applying everywhere? We're not coming up with a new model for a new system. We use the same model for a new system.
Yeah, we're
So we're not generating a new model for a new system. Is that kind of the idea?
Yeah, so we cannot simply sample new parameters from the huge parameter space to represent a new catchment system. We have to train from the start, which is considered to be like P, Y given X.
Essentially, I think all we're saying is that we're representing the model as a deterministic function as opposed to a probabilistic function. That seems to be the only main distinction here. In other words, there's no randomness involved in the generation of the final output.
Yeah. Once the model is trained, they cannot be applied to new places without further training. We cannot simply sample from a distribution.
So if I could go back to your initial picture of the painting, you don't have to go back there, just
okay.
What we're suggesting is that in a generative model, every time you run the model, you'll get a different result.
Yeah.
Of course, you could fix the random seed and you would always get the same result. But if you allow the random seed to be resampled every time, then you would always get a different answer. Would that make sense? Yeah.
Yeah.
Essentially, every algorithm is fundamentally deterministic. We just have to somehow enter randomness into it. Yeah.
Yes, we have to manually force randomness into the system.
Okay.
I
think that's why there's this confusion between the definitions.
Yeah, the definitions are quite different in different authors' papers, but basically everything that can generate new object can be considered as a generative model.
Yeah.
Yeah. So this one can be also a generative model, but it's very hard to use for new catchment just by randomly sampling parameters.
I mean, if during the training of your deep learning model, you were actually estimating distributions on the parameters like you would in a normal inverse process, then essentially it becomes generative again.
Yes, that's true.
One thing we could also do is use this model that's trained to generate response in hypothetical catchments.
Right.
And add in that stochasticity that way. So we if we know we have a catchment that we have a trained model, and then a catchment we want to generate a response on, and we have some parameters that go in to drive this model, but we are uncertain about those parameters. We can generate a distribution of parameters and generate the distribution of the response over the.
I think that's where Yang's going with this. Yeah.
Yeah.
With this latent vector thing.
That's a good point. Yes. Let's go further. So this page, we review the commonly used type of latent variable generative model, it's the variant I'm going to use. We are going to introduce a latent variable into the system, which is a variable controlling the generation processes, but we cannot observe directly, and we do not know the meaning of the latent variable. We just assume there are some latent variable controlling the generation processes. The commonly used variant including GAN, VAE, variation autoencoders, flow-based method, and diffusion models. I won't go into detail of this method, but you have questions for either of the framework, I can answer you. So basically, we are trying to introduce latent variables. We can sample easily, like we can sample easily. And then through a generator, we can generate new models or new object. This work is based on. So here is our framework, which is learning to generate hydrological models. So we are trying to learn a way to generate new object, and the object is hydrological model. So the problem setup is like this. So we have n catchment in our training data, labeled by 1, 2, 3 until n, and the catchment I is associated with a function fi. So fi predicted a discharge time series y given a time enforcing time series x. So y is a function of f. It's a function of x. X and y are multidimensional and multi-time step. So there, we assume there exists a generator function that given some latent vector z in a latent space, we can generate a function. G is a generator. Zi, which determines the configuration of the generator. Then when providing an input x, it approximates the catchment function fi x. So it means that if we give the generator some configurations, it can approximate the catchment discharge generation function. So they supposed to be a multidimensional vector describing the hydrological characteristics of a catchment. So the key assumption here is that the characteristics of the runoff generation processes of a catchment can be sufficiently well characterized by a small number of variables. We do not know the number of variables, and we do not know how well it can characterize these processes, but this is a basic assumption, and it's the only assumption we are going to use to develop generative model. The model we are training is the generator function G, and the distribution of the latent vector Z. Here is a concrete.
Just so I'm following along. So there exists a generator function G that, given a vector Zi, generates a function G of Zi x, which would be, one intermediate step would be, which would be G of x given Zi, and that would be your Fi of x. Yes, that would be.
Yeah, they can write it in multiple ways, and Zi can also go to the subscript of G.
Okay.
That's a configuration of the generators.
But the implication is there is a specific function G, and you just have to condition that on some of the variables to get the F. Yeah. So it's this.
Yes.
It's one generic function. Yeah. Okay.
Yeah, generic functions, which is written in this way. Yeah. So here is a concrete examples. So we have suppose the model only have parameters in 2D space, Zi, Z1 and Z2. Then from the random distributions, we can sample a point, which is like GZ1 and GZ1 to note that this Z is like in bold font, and this is a small z. So this means it's in a vector z. So we can generate different functions by simply sampling from the random sampling space. For each random generated functions, we can supply climate forcing time series X, and we will produce some discharge time series Y. So this is the overall framework, which looks quite simple, but still may not be easy to understand. So let's have some fun and easy to understand way. So suppose we have a generator, a cat picture generator that can generate cat pictures, and the Z1 and Z2 are axes may be related to the style of the cat's painting or the cat postures. If we sample from the point, if we're sampling from this random space, we hope to get a realistic looking cat pictures. And the eventual goal is that if we sample many samples from this space, we hope we can have a library of cat pictures that resemble all the real world cats. In the same way that if we sample from our catchment function generators, we hope that the generated catchment function can resemble all the real world catchment we observed. So this is the ultimate goal of these generators. So Jonathan?
Yeah, I understand this is a very this is an example just for like an analogy, but so there's some space on that plot on the left that doesn't resemble a cat, and then there's some discrete space on the plot that will not produce a cat, and there's some discrete space on that plot that will produce a cat. So there's some ISO line, or there's some sort of subspace in the plot on the left that will produce a realistic looking cat. So
yeah.
Okay, I guess I'm wondering if there's a dimensionality. How far does this analogy go in terms of the dimension? Because we're thinking about the hydrological models with the two variable spaces. So it's the groundwater and then the capacity. So it's just two variables here. But in this cat example, does the dimensionality work out as well? Or is this analogy a projection of a much higher dimensionality for the cat example?
Okay, so Jonathan, thank you for the question. I think you are absolutely right about the dimensionality and the gaps of the point. So the goal of generative AI is to find a model that can generate from any point of this space, like to produce a realistic looking cat, but with low probability point, like on the edge, the cat may look like a cat, but also look like a dog, so to say, because it's low probability. Maybe in somewhere in the world there a cat look like a dog. And regarding the dimensionality, so the dimensionality, the 2 dimensions example for the catchments are only hypothetical. In our model training, we treat it as a hyperparameter we can tune, and the exact meaning of each dimension is unknown. We do not know the exact meaning of each dimension, which is almost always true for the generative AI. The dimension are unknown. The exact meaning are unknown unless using specific regularization method. For example, we can enforce following certain directions the cats to be more brownish or more yellow. And similarly for catchment, we can enforce some certain dimension to represent catchment storage capacity. But it's commonly it's a technique that has not been applied everywhere. We just naturally forcing the space to always produce meaningful new object, unless it is floating into like very unlikely places. We do have some point, like some gaps, which we cannot have meaningful object being generated. But that is the flaw we want to overcome. The goal is to have a smooth space. From each point, we can sample a meaningful image or meaningful object. So, okay.
Leela has a hand up.
Leila?
Yes,
go.
Yang, if you have gaps in your time series data that you use as an input, what will happen to the generative model?
Sorry, Leila, could you
Yes. If you have time series data that has gaps, and
Gaps.
so yes, will the generative model be able to identify the gaps in your time series in your input data, so it won't be biased towards those gaps?
I think for now, in this current study, we did not consider gaps, and our models are about generating hydrological modeling functions. So the functions can be applied even there are gaps. But for now, we assume catchment characteristics can be summarized in lower dimension, like 8 dimension or 10 dimension, each dimension representing a certain catchment characteristics, like how fast it responds to a rainfall input and storage capacity, flashiness, etc.
Okay, thank you, Jen.
Okay, thank you, Hoshin.
Can you go back to your cat picture?
Okay.
So to me, the important thing over here is recognizing that each point in your vector space is a vector. So you actually have to think of it as a high-dimensional vector, and you've got a density of vectors, and you're assuming some kind of smoothness and continuity in the variation of the vectors. That's
Yes.
one of the assumptions. The second is I think the analogy is that this is like, instead of thinking of this as cats, you can think of this as cat-like behaviors. And so given a particular prompt, like a dog approaching, each of these cat images actually represents a cat response. And that would be our analogy to catchments. So there's a particular function which mediates the input into the output. So it's perhaps a little bit better to think of these as cat-like behaviors that we're modeling, as opposed to cats as objects per se. Yeah.
Okay. Yeah, thank you for these suggestions. Okay, so I think for now, the cat pictures can also be considered as a function, like x, y coordinates function, and the y is the color, but it's uncommon. Yeah, so we are generating functions, and these are real numerical object, numerical multi-dimensional vectors, essentially, for each image. Okay, so let's go to the next one. So we hope our generators can also be used for modeling any catchment. So in this way, we need to accomplish this task, we hope our generator can identify a point in the multidimensional space that produce a image or a model that has small distance or close to a real world object. For example, given a real world cat, we hope by searching through the space, we can identify an image generated by the model that can resemble the real world cat. Similarly, for a given catchment, we hope that by searching through the space, we can produce a hydrological model that resembles the real world catchment function. So this is similar to search algorithms for optimizing the parameters for the lump hydrological model. It's just interpreted differently. Okay, so let's see how the generative model is trained. So for the n catchment we have, we assign each catchment a code, which is one hot embedding method. If you are familiar with machine learning, so basically for catchment 1, we assign a n-dimensional vector. At the first position, it has a value of 1, and the rest of the position the value is 0. For catchment 2, similarly, the position 2 is 1. Other positions are all 0. Then we pass this giant matrix into into an embedding network. It will produce for each catchment a d-dimensional, which is the lower dimensional embedding, like n-dimensional code, 1000 into a 4 digits, four number code. And this embedding matrix, for example, we can choose a catchment number 2, which is corresponding to these 4 numbers, and we feed these 4 numbers together with the climate forcing, and through the generator function G, we can get the predicted runoff of catchment number 2. Now we compare with the observed catchment number 2. Get some errors. The error can be used to update the parameters of the embedding network and also the predictor network. So both G and the parameters of the embedding will be updated. So during training, we will train many times for all the catchments. So the model will be optimum. The embeddings and also the predictor networks will be optimum for all the catchments. So this is similar to the previous cat pictures that the generators resemble almost all the real world catchment, almost all the real world cats. If we have a sufficiently large samples. Note here that this work is different from the previous work because we do not use catchment attributes. For example, topographic characteristics, climatic indexes, soil characteristics, river network, etc. We assume we assume all the necessary characteristics that needed for defining a runoff generation model can be thoroughly extracted from rainfall runoff time series record without relying on the catchment attribute. So this is our assumption. And the architecture of the generative model is also very simple. It's a generator network G. It's also very simple, but it can be more complex. We use a simple arXiv framework. So this is a catchment latent vector 4-dimension for catchment I. Then we have a multi-time step climate forcing time series for the catchment. We repeat the latent vector vectors multiple times and concatenate with the time series input X. So we expand the dimension of the climate time series. Then we feed in a arXiv network parameterized by theta, which is like a parameter of G, the generator G. Then we get the predicted runoff time series. So it's quite simple and quite generic model framework. And to calibration, after the model is trained, we can apply to arbitrary catchment by searching through this parameter space, just like we are doing model calibration for the conventional models. Because a generative model only use a few parameters to describe a catchment, which is the same as the conventional models. We do not need to know the meaning of each dimension. We just need to search through the space, like 2D space. We just need to search through the space to identify the global minimum, maximum fitness. So I will not discuss how we can do model calibration, but it's the same as the conventional model. Any generic calibration tool will work. So for training our model, we are using a global dataset, Caravan, which we use 3,000 catchments. The catchment we select are excluding catchment from the US and catchment from Switzerland and other regions for model testing purposes. We only train the model outside the US and outside of Switzerland. And for camels, which is like US-based catchment, and camels CH, Switzerland catchment, we use them for model for testing our model, which is performance during calibration, or performance for novel new catchment. They are not used for training the generator functions. They are also hyperparameter optimization processes, including the dimension of the latent space, neural network shape, learning rate, training iterations, etc. We are using Bayesian optimizations using a trend validation and a test split. So those are technical details I won't go into deep. So Joseph, you have any questions? Joseph? I think you are mute, Joseph.
He took his hand down. I don't know.
Okay. So, okay, let's continue. Joseph, if you have any question, just ask. Oh, I saw in the chat.
Can you post your question in the chat? We can read it.
Okay. I can answer you if you put your questions in the chat as well.
Just to clarify, Yang, so you use the Caravan dataset for training and then the camels and camels Chui for testing.
Yeah, for testing, but testing, there are two ways of testing. One is testing on the catchment that used to train the generator, which is like similar to original study. Another one is to out sample testing. Out sample testing meaning we have already trained our model framework, model structures. We want to test on novel new catchments.
Right. So the 559 and the 157, those are the catchments which were not used in training.
Not used in training at all, yeah.
Okay,
Only do calibrations.
Sorry, I don't understand what you mean by calibration.
Calibration is the term that is being used. I mean, calibration means we only calibrate the latent space dimension for each catchment. We do not need to retrain the parameters. We only estimate the optimum parameters for each catchment, which is similar to conventional hydrological model calibrations. Maybe we should find a better name. It's also very confusing to me.
Okay, I'd like to continue and come back because that part's a little confusing here.
Yeah, calibration. Yeah, okay. So the result is that we train on 3,000 catchment outside US and Switzerland. We find out the optimal latent space dimension is 8. So which means we can sufficiently well characterize the catchment function using only 8 variables. The candidate values are 2, 8, 2, 4, 8, and 16. We try to keep it low because the conventional models, the parameter number are also low. And this plot will show the prediction accuracies for the test period and the training period for 3,000 catchment, and the median prediction accuracy is 0.69, and the test median is 0.65, which is reasonable considering it's a global catchment study, but it can still be improved. We did not analyze when where the model perform poorly or perform good, but it can be further studied. And there's also a performance gap can be observed between the training and test set. It suggests that there's a slight overfitting, which can be caused by the reasons that the training and the test data are from different period. The catchment properties may change or may shift, but we need further study to confirm that. We show the performance of different regions in this slide. We can see that in some areas, for example, in Great Britain and Central Europe region, in Central Europe and in Great Britain, the model performed quite good. Maybe the data quality was good, maybe not. So the KG, the training and the test are both about 0 in Great Britain. And in some other areas, for example, in Brazil, during test period, the KG can be much, much worse, like -8. We still need to find a reason to explain for each individual catchment, but it's left for future work. And this is a calibration part. So after our model is trained, to apply for a new catchment, we only need to search through the space to identify the 8 optimum parameters. We do not need to retrain the model. So this is called calibration. We compare the model calibration efficiency with 36 types of conventional long-term models, including POP model, GR4G, Xinanjiang model, and tank model, Wake model, etc. Like 36 types of commonly used hydrological models. We go into the same procedures, which is searching through the parameter space to identify the optimum parameters. We do this for the Camel's catchment, 505.
Okay, so now I'm understanding. So this is the mapping from the latent vector space to the parameter space of those conceptual models.
Could you repeat?
So you determined your latent vector representation, which has a dimension of 8.
Yes.
And then you use another procedure to say, if I have a particular model, GR4J, what would this latent vector space correspond to in terms of values of parameters for that GR4J model? So you're doing a mapping from the latent vector space to the parameter space for GR4J?
No, we did not do that. This slide is only showing that we do model calibrations for the US, for the catchment in the US, using the same procedure for the lumped model and our generative model. We are calibrating these 37 types of models using the same procedure, genetic algorithms. For each, for example, GR4G has 4 parameters. We just simply, for each catchment, we estimate the best 4 parameters for that catchment.
Got it. So now for a catchment, you have 8 latent vectors and you have 4 model parameters.
Yes. Then we compare the prediction accuracies in the test period.
Okay. Go ahead. Yeah.
Yeah. So yeah, the term is quite confusing. Calibration, yeah. We need to find a better way to describe. But eventually we are comparing the models in real world applications after calibration, how it will perform in test period.
Yes.
Okay, so for the camels catchment, we compare our generative model with the conventional models. The test KG median is 0.737, which is quite high. And you can see the cumulative distribution curve, CDF, our generative model perform better than any conventional model in general.
So each of the gray lines is a different model. Okay, got it.
Each gray line represents a conventional model.
Got it.
Like Xianjiang model, GR4G model, yeah, or our model perform the best when applied to a new catchment. We only need to estimate 8 parameters using generic algorithms. And for the camels catchment in Switzerland, camel CH, our model also has good performance. And one thing to know that is our latent space is not very smooth. Doing search multiple times will have different result. Jonathan was right that our space should be smooth. There are some holes corresponding to non-generative, like non-realistic object. So we will try and fix that in the future. For now, our model is not very stable, but this result is only this result is quite fair comparison because we only run our model once for calibration. We did not run for multiple times. Select the best one. It's only one it's only one random genetic algorithm run. So if we run multiple times, the result can be bad. We compare the rankings of our models among the 37 types of considered models. So in almost half of the cases, our model surpassed the best lumped model. So it is a perform number 1 out of the 37 model, and it has majority of cases to have top 10 performance out of the 37 models. And we compare our generative models KGE, test period KGE, with the best conventional model instances. We find that in some cases, the best out of the 36 conventional lumped models can have much better performance than our generative model instances. For example, our model can have negative scores, but for the conventional model, it still have KG scores above 0.75, which suggests that lumped models are still very useful in some catchments. They can still have better performance than our generative model. Although if we look at the cumulative distribution curve, our model seems to be the best. But for some catchment, our model perform much worse than the lumped models, which is using physical principles to build and develop. This is spatial distribution of our models KG for the test period over the US. We can, and this KG group indicate the performance. If it's below negative 0.0414 means that the model performs worse than using the mean as a predictor. So the model perform poorly in the regions in the central and west US. And the darker the color, the poorer the performance. And we also compare our models, the difference between our model compared to the best lambda model. We found that in the East Coast and the West Coast, our model has a better performance as indicated by the greenish color, which means our model is better than the best lambda model. And in the central and west US, our model can perform significantly worse, as indicated by the reddish color. And so the effect and the exact meaning of each dimension of the latent space is currently unclear. We do not know like the meaning of each dimension, but we can change the dimension, the value of each dimension to see how the response changes. For example, in dimension 1, if we change the parameters by increasing it by 50%, we can see an increase in peak discharge for large discharge event, but not for the smaller event. For dimension 6, if we increase or decrease the parameter value, the prediction does not change much, and the model has some more sensitive to some dimension and not sensitive to other dimensions. But the model, each dimension is not orthogonal to each other, so it may be very difficult to analyze the sensitivity of the parameters. They can be used, studying the sensitivity of the parameters can be done in future studies. Here is another result. We tried, which is in collaboration with my colleague from the University of Washington, Dr. Jiang Long. So the title is wrong, so sorry. So for this one, basically we are comparing the pairwise distance between catchment in their physical space, which is showing the x-axis. One point represents a pair of catchment. So this point means two catchments are close to each other, and this point means two catchments are far away from each other in their physical property space, normalized physical property space. And the y-axis shows the normalized distance between their parameter space, the generative models parameter space, the optimal 8 parameter values for each dimension. For each catchment, we calculate the pairwise distance between the catchments in the US. We find a linear, almost very good linear relationship with some exceptions. This means generative AI can capture the similarities between catchments, between catchment physical property space, meaning that if the two catchments are physically similar, their parameters will also be similar in our generative models.
By physical properties, you mean static characteristics?
The characteristics, yes, the ones provided by camels,
Okay.
like soil type, etc. But this one, but for this study, we use almost all the attributes provided in catchment in camels, which we can narrow down and do a detailed study how this how the parameter similarity align with physical property similarity in a detailed way. And we also compare the result with other conventional models. This surpasses many conventional, our model surpasses many conventional models in terms of the alignment between physical property and parameter space property and parameter similarity.
What's the dimension of the static properties or the physical properties? It's like in the 30s or something.
I'm not sure. I think 30 could be a reasonable number.
So you're going from 30 down to 8 and preserving this property, this linear, almost linear relationship. Okay.
Yes. And its preserving alignment is better than conventional models. I think we are only in the 36, we are top 5 or top 10. I'm not sure. I cannot remember.
Sorry, these are the calibrated model parameters or the latent vectors?
Calibrated latent parameter values for each catchment.
For the generative model, not for the physical.
For generative model, yes. The y-axis for generative model. We have plot for the lumped model as well, but we did not show. Then we calculate the correlation coefficient. Then we compare whether we have a stronger correlation than the conventional model or not.
You have those plots in the paper or no?
No, this is an additional study to this paper. It's not included in the paper.
Okay.
It's still ongoing. So we are hoping to present some new results during the HydroML conference. There will be a poster. We can send you the poster result to you. But the project is mainly led by Dr. Jiang Long. It's not by me.
Got it.
Okay. Okay. Thank you for the feedback. I think the result is quite good and unexpected. The linear relationship is so good.
Yep.
And so here is our overall framework. How can the generative model fit in the latent vector modeling framework? So in our previous paper, we described that for different catchment and different hydrological model instances, we can summarize or capture their runoff generation characteristics in a low-dimensional space, that by measuring their distance, we can determine their fitness without running the model. But there are going to be many holes in this space, as we cannot find a perfect matching model for each catchment. So by generative AI, we are hoping to fill up these holes to provide more options for modeling catchment, such that we can find a nearby model instances for a given catchment. So by model instances here, we mean both the combinations of model structure and the model parameter, which is a concrete function that can be readily used for hydrological predictions. So we are hoping that in this space, each catchment is nearby a function that can be used for predictions. We are hoping that by our generative modeling framework, we can generate more modeling functions that can fill up the empty space within the lower dimensional embedding space of the catchment hydrological functions. So for future work, we can conduct larger scale studies with more catchment. We can try different neural network architectures. So here we are using simple LSTM, and we can add regularization to latent space to improve its smoothness so that every point is meaningful. And there are some advanced new directions, which is try to add interpretabilities into the latent space such that we can know the meaning of each dimension, or we can command, like write some instructions for the generator to generate a specific function that has certain properties. For example, please give me a catchment that has fast response to flood event, etc. And then we can add stochasticity and randomness into latent variable representation to account for uncertainty. We can also integrate the generative model into a latent space modeling framework I mentioned in the previous slides. So the conclusion of this study is that generative modeling provide a way to automatically learn a general model from data. So we learn a general model that works for the global catchment from the data. It requires only a fundamental assumption, which is that the complexity of the hydrological characteristics can be summarized using a limited number of numbers of variables, and we did not use human-derived hydrological knowledge in developing the generative model. And the model can be used the same way as conventional lumped model and can achieve good performance and good prediction accuracies. And the second conclusion is that a small number of latent variables can adequately describe the catchment characteristics in terms of runoff generation processes. And I think that's all I'm going to talk today. So thank you. If you have any questions, please ask or anything you want to discuss. And the link to the paper and link to the web applications are in the QR code. Thank you.
Joseph's question is in the chat now. Yeah.
Okay, let me check. Let me check.
He says the original camels was by Ador. Is the Nobbin camels different?
Okay. Okay, I think the orders camels does not include evapotranspirations estimation like PET, and Nobbin calculate the potential evapotranspiration PET. I use his version instead of calculation my own. Instead of calculating my own, is because that for the comparison study, for the benchmark study, he used his own derivations. So to be consistent, I use his version. Okay, Tao Liu, please.
Can you hear me?
Yeah, I can hear you clearly.
Okay, good. Yeah, nice talk. And I
Thank you.
just read your paper. Yeah, there are a couple of questions. Let's see which one okay. So maybe my understanding is totally wrong, but after reading the paper and after this talk, it sounds like this generative model is very similar to the LSTM model plus the static basin features or attributes. You replace those attributes with 8 latent variables. Yeah, this is just my sense. So how about we use both these latent variables and the basin static attributes? And also this latent attributes is kind of like the like random multipliers to minimize the function. Yeah, just something random thoughts and questions, and I'd like to have your thoughts on this feelings.
Okay, thank you for the question. I think you're right. The architecture is very similar to the multi-catchment LSTM. The only difference is that we do not use catchment static attribute, because I think the difference is that the fundamental assumption is different. So in their assumption that the catchment attributes are informative, so that it can help the LSTM network to differentiate between different catchment hydrological functions to make better predictions. Our assumption is that we can solely learn the characteristics of a catchment's hydrological function only using the recorded time series, like rainfall runtime series. And another difference is that our model is generative. We can use for a new catchment, like a random catchment, we can just estimate the 8 parameter values without the need to retrain the model. And I understand for their model, they can apply directly the new catchment attribute to get a new prediction model, but the prediction accuracy for their approach is not very high. So that's my response. Thank you.
Mhm.
Please.
And I also have another question. I'm not quite understand the slide you said, the Jianglong leaded research. What do you mean by the normalized distance between the physical properties of like the catchment pairs?
Okay, so so this is a pairwise distance shown in this plot. For example, this 10 means that the two catchment, a pair of catchment has a distance of 10 in the normalized parameter space. The normalized parameter space which means that we have for example, we have 30 parameters. For each parameter, we normalize into a range between 0 and 1.
Mm-hmm.
So we calculate the distance in this normalized space, which is like from 0 to 1 in all 30 dimensions. We calculate that distance after normalization. Similarly, we do this for the optimal model parameters in our generative model, and we find a linear correlation.
You normalize by the population of all catchments.
Normalized by the maximum and minimum values of all the catchments. Yeah.
Okay, so yeah, then this nice figure give me just a like, okay, this generative model can tell us the static feature, like the watershed attributes. Can we understand it that way? Like if you have a larger distance in your model space, variable space, and you will have a larger the basin attribute space.
Yeah, you can. Yeah. Yeah, I think your interpretation.
With the caveat that you're going from a 30-something dimensional space down to 8. So when you go from 8 back to 30, you're not going to have a unique mapping.
Mm. Okay. Wow, cool.
Joseph?
Okay, thank you.
Thank you, Todd. Thank you. We have Joseph.
Yeah, thanks for the talk. So one of the recent papers I worked on is about predicting kind of water table depth. And one of the reasons that machine learning fails in that context is we have an extremely biased representation of observations in groundwater. So all of our observations are in like low-lying areas and not too hot, not too cold, and you only measure the water table where we expect there to be water, or else you wouldn't drill a well. And I would kind of expect maybe something similar in your context, maybe not as severe, but when you have that example of pictures of cats, we have a lot of different pictures of cats, and the whole kind of distribution of pictures really represents the population of cats. But in hydrology, I mean, I'd expect our observations of catchments to be quite biased towards places near cities that are kind of on coastlines, and again, not in super hot places, not in super cold places, not in Antarctica or whatever. So, and not on Mars or another galaxy. So do you expect, like, I feel you have that one representation of the surface of all catchments towards the end of your talk. And, you know, of the caravan catchments, you know, we might only be sampling some small portion of that, even though any combination of parameters would give you a realistic catchment, even though we might not have sampled that catchment. So do you anticipate any problems there, like sampling bias problems?
Yeah, I think that's thank you, Joseph, for asking this question. I think sampling bias is definitely an important problem to consider in generative AI modeling. If our model did not see a catchment like in a cold region, I suspect that it will not generate a model that can model a cold region catchments. I think that's why we mentioned in our future work we should conduct a larger scale study to include more catchment in different regions, smaller or larger catchment. Maybe it may be useful to build multiple generators for different kinds of catchment, or maybe we try a large generator for all the catchment. So those are questions we need to understand, and the power or the information carried by a new catchment, we still need to understand and quantify. Like basically, we want to understand how many catchment from each region we need to be able to extrapolate reliably for catchment in the similar regions. And I think that those are important questions for future studies.
So like the basis of your work is kind of saying that only certain combinations of your latent parameters or of your latent space are realistic. Like you have that surface of kind of realistic catchments in the previous slide. Do you think that's meaningful? I mean, we have, you know, if you looked at caravan and you have the correlation between temperature and precipitation, we're going to have some correlation there. And you might say like, okay, so we have, given these two attributes, we know that only that realistic catchments can only follow this kind of narrow line of this relationship between these two attributes. But there's not really any fundamental reason why it can't be outside it. You know, we just
there's physical limits to what these are representing. So like a groundwater infiltration parameter is representing something that would be that would be bound by physical limits. And so when you take these like dimensional reductions, those are also have to be bound by the physical limits. So I would actually argue that there are these subsets that you have to subset that in order to represent a physically realistic system.
If I could suggest, and then looking at this by analogy might be helpful. When we train generative models on painters and paintings, we can only learn models that are capable, to some extent, of reproducing the styles of those painters and interpolating between them. And we learn a certain dimensionality to represent them. So our models are typically only going to function in the space of paintings that the model has been given. Now, if you give it enough examples, you might hope that it would learn the underlying principles of what constitutes painting, and thereby hopefully extrapolate outside the range. Although you might be limited by the fact that in order to do a novel painting, you would have to add a new dimension, a new latent vector or something like that. And, it's possible that your training set might include very few examples of some very radical outlier painter. And so it would ignore them when building the model. So I think there's a very strong analogy here in that sense that what we're trying to learn is a space, but by and large, what we're really learning is an interpolative space. And we have to be very careful when we try to extrapolate.
Yeah, thanks for the discussion.
Yeah, thanks for the discussions.
What I do find interesting, I wanted your comment on this, Yang, is that in a sense, what we're saying is that we can encode the functional characteristics of a catchment with a genetic code which has 8 values.
Yeah.
It's like saying I've got a genetic code, right? I've got these 8 values, and those 8 values, when decoded by some decoding mechanism, so the 8 values don't exist. They don't exist outside of the fact that they also need a decoding mechanism to convert those 8 values into functional forms, which then map the input to the output space, the input to the state to the output, right? So those 8 values sort of exist in the context of an encoding decoding framework that we have constructed. And if we just take those 8 values, if we're lucky, you might be able to use them and reinvent the encoding decoding framework, but we're not entirely sure about that, right? So, I mean, if I just gave you the 8 values and said, here are your 3,000 catchments, and I can represent each catchment as a dot in an 8-dimensional space, right? It's a vector in an 8-dimensional space. Hopefully that, as you've shown in your example over there, hopefully those vectors obey certain embedding rules so that 2 vectors which are close together represent similar catchments, and 2 vectors that are far away represent different catchments. And if you take the analogy from large language models, if you were to add vectors together, if you had a vector for one catchment and you added a vector for another catchment, you would get a vector for a third catchment, which is some combination or compound. In other words, there has to be some vector space embedding rules that the embedding has to obey in order for us to actually then be able to do meaningful interpretation on it. Yeah.
Yes. I think there's a field study the geometry of the latent space, how the point move change the properties of the generated object or the corresponding functions. I think it's quite an emerging field, like studying the geometry of the embedded space.
So what this is helping me with is I've always wondered about the relationship between functions and parameters, right? So actually, a function is a particular functional form. It restricts you to a particular manifold in the space, the input in the mapping space. And then the parameter chooses which specific realization of that function. And so it's in some way, there's not actually a separation between functions and parameters. They exist in a continuous space, and therefore, in principle, should be representable as a set of numbers. In other words, I could give you a set of numbers. It should, in some sense, tell me what the function is and the parameter values. It should be a way of characterizing the entire shape of that function.
Yeah.
That's a new one for me to think about, but that's very interesting. Yeah. All boils down to encoding at some level.
Yeah, actually the results are quite also surprising to me. So the model kind of work so well. It's only 8 parameters. So I intentionally choose the candidate parameter value to be below 20, because in most current lumped models, they have fewer parameters less than 20, fewer parameters than 20.
Wouldn't it be more, sorry, Joseph, just one sec. Wouldn't it be more accurate to say that on average, your result, because you're training over multiple catchments and you're looking for minimizing the error over multiple catchments. So you're basically saying we expect about 8, but some catchments might need more and some catchments might need less.
Yeah, that's true. That's true.
Sorry, Joseph, go ahead.
Joseph?
Yeah, the outliers in slide 27. Do you see any particular pattern in them with respect to the NSE of the generative model versus other lumped models? Like, does the generative model do particularly well there, or particularly bad there? Do you know?
I did not look into the details. Sorry for that. But I also find this point to be strange. Maybe it is due to the optimization stuck into a local minimum. So for two catchments that are physically very similar, our optimizer, like genetic algorithm, propose two set of very different model parameters. Maybe it's because our optimizer stuck in the local minimum. We may need to repeat the optimization to figure out. Similarly, we also need to repeat optimization processes for the calibrated model as well. But that's also a problem of how to represent the average result. Should we pick the best one or pick the average one? Because for model calibration, each time the result can be different.
But I also find it strange that they all fall at exactly the same value of normalized distance of physical properties, which suggests there might be some errors in the data set on physical properties.
It could be some errors as well. Or could be our model hitting the optimization bound. We have a lower bound and upper bound. Maybe.
Yeah, but wouldn't you expect, you've got, I don't know, 10 or 15 or 20 catchments there, and the distance is exactly the same. That sounds very, very suspicious.
Mm-hmm.
Yeah, this is a pairwise distance, which is like one catchment similar to another catchment. Yeah, this may be something wrong about the data. Yeah, we'll have to find out.
I mean, I would expect some scatter in the X direction, but you're not seeing any scatter in the X direction.
Yeah, this is strange. Let me check with Dr. Jiang. Dr. Jiang.
Leila?
Yes. Thank you, John, for the discussion. And it makes me think also in the relationship between a structure and function. And so I have a question regarding if you have thought about how much information a particular latent space holds. Like if you change your latent space, can you compare how informative is one latent space in comparison to another one? I mean, if you keep adding watersheds to your current latent space, would that means that you will have like a much more informative latent space, and therefore you will be able to predict the behavior of any other?
Okay, I think that's a very interesting question. That by adding more data, will our space change in shape or in dimensions, or will the geometry of the space will change? Will the catchment not lying in the low dimensional embedding? Or I actually do not have the answers. I think this can be an interesting question to study in the future. But I suppose by having a higher dimension, by adding adding additional dimension, if we add more catchment, the risk of the average distance will be even larger between catchments, because there's a famous law called like curse of dimensionality. If you add more dimensions, all the points within all the points within the space will have a large distance, because the dimension is so high it can be hardly filled up by the point. The curse of dimensionality arises here. So maybe we should keep the latent space to be low but simply adding more point rather than increasing the dimensionality. Yeah, I'm not sure about my answer satisfy you, but we can explore together in the future.
Thank you, Jan.
Thank you, Laila. Hoshin,
Yang, can you go to slide 26?
26, yes.
So this discussion reminded me of this figure over here. If you look at dimension 6,
Okay.
okay, just based on this data, of course, this is only a limited portion of the data, this suggests that dimension 6 is irrelevant for this catchment.
Yes.
And dimension 5 is only slightly relevant, yeah?
But the
So this
7 is very.
So it sort of suggests that for some catchments, 8 is too much, right? And it's quite possible that if you were to go to some catchments where the match was not as good, the performance was not as good, it might, a speculation would be that if you increase the dimension on those catchments, you might actually be able to improve performance. In other words, by restricting all catchments to 8, you are regularizing things in such a way that it works well in some cases, but not in others. So it might be interesting to find a way to have a variable dimension latent space at some point in the future, which accounts for performance, right? It sort of grows or diminishes with.
Yeah, that's a great suggestion. Let me show you our real-time. Let's see, for the other catchment, let's randomly choose one. Number 6, where it change the shape. It will change the shape for other catchment.
Yeah.
Parameter 6. Yeah, so yeah, I think it's useful to do a variable latent space number, but it can be challenging. Let's see how it unfolds.
Now, something for the future. I'm just saying, the suggestion of 8 almost implies a common description length of complexity for all catchments. And as a starting point, that of course makes sense, but as we go into the future, that might not make sense, right? Yeah.
Yeah.
In some sense, what we're looking for is the change in complexity from input to output, right?
Yeah.
And that change in complexity is presumably moderated by the catchment. So.
Sure.
Oh, based on this observation, do you think there is a way to connect this 8, or you may have a variable to account 8 or 7, or maybe even less, those values to the, let's see, the basin's elevation or climate, or those attributes some way? If we can decipher the model in that way, we can also use this method on other ungauged area.
Yeah. I think so. I think that's a good direction to go. We can try to predict the parameter values using catchment attributes, which is being commonly done for lumped models, for ungauged catchment model. We can do the same for our generative model. I'm not sure how the result will be, but from this figure, it seems to be reasonable because there's a correlation or explanations between the variations among catchments align so well. maybe it will have better performance than the conventional model. Yeah, but yeah, maybe it will be useful in the future. But for now, I'm doing a separate study that is only summarizing catchment characteristics, not the model, which means that for each catchment, it has certain location in the space, and it is not the same as the model. It has some distance, so we should consider the distance when predicting. So, for example, for this catchment number 1, the optimal model is a star, and the star has some attributes. We hope that the attribute of the catchment will predict the attribute of the star, but actually there are some distance. So for now, I'm trying to predict the attribute, the location of the catchment in this latent space using its attribute, rather than the location of the closest model in this latent space using the catchment attributes. So for now, for my current study, I additionally consider the distance between a catchment and the model instances. Yeah, but yeah, this is very it's not we can do it offline for additional talk.
Yeah, sure.
So
are you going to go to the Hydro MLs in Richland this year?
Yeah,
Next month? This month. Yeah.
This month, yeah, I'm going to HydroML, and you will hear the talk again. I'm sorry. There will be a tutorial on this one.
Cool.
Mostly the same.
Yeah. I see that. Yes.
I will teach you how to write code for training this model.
Cool.
I mean,
Yeah.
you can skip the first part and come back and the coding.
Glad to learn. Yeah.
So Yang, we got a long time, and I know it's late for you. Just one final comment, and we should probably let you go. Can you go back to 26 again?
26. Okay.
So what this makes me think of is that the problem that we're facing is that if we go from catchments and we describe them as static attributes, just for a moment, those static attributes are not independent dimensions. They are highly correlated. Yeah. Similarly, when we look at the hydrograph, the time series of the hydrograph is the independent points are not independent. The individual time steps are not independent. They're highly correlated. And when we go to generative AI for pictures and stuff, they figured out a way to figure out how to regularize the latent space in such a way that when you turn a particular knob, it changes only a very specific characteristic, like the angle, the rotation, the color, the texture, and so on. So we're looking for something similar here, right? And it sounds like what we need to do is, instead of looking at hydrographs, we need to be looking at lower dimensional encodings of hydrographs, where each dimension represents a different behavior of the hydrograph, like a peak going up and down, or a recession changing, or something like that, right? And then we need the same thing in the latent space. We need the latent space vectors to be relatively independent. And then maybe we can get to the point where changing a particular latent vector changes, and we can say it changes a particular observed aspect of the hydrograph, right? The problem right now is we're working in these highly correlated spaces.
Yeah, thank you for the comment. I think in the future, we are hoping we can decipher or understand what each dimension mean, or we can design a space that we understand each dimension, so we can fine-tune the model we generate.
Right.
This paper is only a first step to introduce generative AI into generating functions, modeling functions.
Sure. I mean, if you go back historically, before we had computers, we sort of had 3 or 4 dimensions. One was time to peak. The second was the peak. The third was the volume under the hydrograph. And then the fourth might be the recession rate. So there are sort of attributes where each hydrograph can actually be reduced to certain properties which are actually meaningful, right? And I think we have to go back to thinking the way we were thinking in some sense before we had computers to make things easier for us.
That's
All
true.
right, Leela, back to you. I think we should let Yang off the hook here. He's been going almost 2 hours.
Yeah, thank you, Yang, again. And yeah, I think that is all for today. We are gonna see each other in 3 weeks and before going to HydroML. And so thank you, everyone, and see you in 3 weeks.
All right. I'll see you
Thank
in
you.
that, Yang.
Bye-bye.
Bye. See you.
Bye.